Hey everybody. So I'm going to walk through the practice exam, give you a sense of how to answer these questions so that whenever you get to your actual exam, you have a little bit more context and it's a nice little review, or I hope that it's a nice little review. So this first question is calculate the PI of the amino acid lysine. In order to answer this question, you need to know that lysine is represented by the capital letter K. The single letter code for lysine is K. Now, what I always like to do is I like to take the single letter, I'll write K there, and then on a piece of paper, I'll write the N terminal, C terminal, and R value, pKs. So lysine being on the 8.95 on the N termini, R group is 10.53 and 2.18. The next thing that I'm going to do, so here's my little model. The next thing that I'm going to do is I'm going to write the possible charges. As a positively charged amino acid, this can have a charge of +2. It could also be +1. It can be 0, and it can be -1. Now, anytime that I encounter a triprotic amino acid or a triprotic molecule, well, I have 3 pKa's. What I'm going to do is I'm going to list them in increasing order. So 2.18, then 8.95, and then 10.53. Those are my pKa's. 2.18, 8.95, 10.53. Now, the pKa's that I care about for this are 8.95 and 10.53. I'll pull up my calculator and I'll say 8.95 plus 10.53. I'll divide that by 2, and lo and behold, I get 9.74. Okay, so that's what I'm thinking there. Now, if I look at my different answer options, I'll give you a little bit of a kind of an idea how to anticipate these answers. Now, the numbers down below are the other answer options. Well, I've got 6.36, 7.22. Now, I think a good way to come up with a number is to or good way to come up with a bad answer is to expect the way that people do these calculations incorrectly. One way that they do it is they add up all the pKa values and they divide by 3, or they divide by 2. Now, none of these answers are correct. That's totally there as that's totally not correct. 6.36, if I remember correctly, that is what you would get if you took 8.95 and 2.18 and divided those by 2. That makes sense. The difference there is about 73.5, so that's 5.6. Yeah, so it's about 6.36. So that's what you should anticipate for this sort of question. Now, the next question reads, and actually, I'm going to go ahead and press cancel here. I'm going to use this table, and you'll need to use this table or these tables again, maybe. Calculate the PI of the polypeptide AFK. AFK. So what I'm going to do in order to approach this question is I'm going to take my piece of paper that I just worked on and I'm going to move it over. And I'm going to write A, F, and K. Now, I'm going to look at these charts and I'm going to find out my different pKa values. Alanine, A, is a diprotic amino acid. If we look at our rough peptide AFK, we know that there's a peptide bond between A and F. And so there's a peptide bond between the A and the F, as well as between the F and the K. What that means is we don't need the C terminal pKa value for alanine. Okay, so what I'm going to do is I'm going to write down the 9.87. That's my N terminal pKa. I'm going to ignore the 2.35 because that is involved in a peptide bond, and a peptide bond is not ionizable. Now, F, phenylalanine. You'll see that F has 2 pKa values. But lo and behold, when you look at F, that is in the middle of that peptide. So what that means is that the N termini is a part of a peptide bond. The C termini is a part of a peptide bond. So I actually don't need any pKa values from phenylalanine. Lysine, on the other hand. Okay, I don't need my N termini because that's in a peptide bond. My R group, I do need that. That has a pKa of 10.53. The C termini of lysine is 2.18. Okay, now a great question to ask yourself right here, in order to answer this sort of question, think about what is the possible charge of this. I have three groups. One of them is a carboxylic acid. That would be the C termini of my peptide. That carboxylic acid, when it's protonated, has a charge of 0. Okay. Then I have the N termini. When that's protonated, I have a charge of +1. My lysine R group, when that's protonated, I have a charge of +1. So what that means is my molecule can have a possible charge of +2. And then let's think about deprotonating those three groups. We can go from +2 to +1, +1 to 0, 0 to -1. So that gives us our three lines on our number line. And we're going to write those pKs 2.18, 9.87, and 10.53 in increasing order. So there you go. Now, one thing to keep in mind with that is, well, all that we're going to do is we're going to take our calculator, 10.53 plus 9.87 divided by 2, and I get a PI of 10.2. 10.2, 10.20. Okay, my correct answer that's indicated is 10.2. Now, some of these other answer options, let's make sure that I didn't make any duplicate ones on there. 6.36, 7.22. Okay, yeah, there are some duplicates, but essentially these wrong answers, what they include are some of the N termini, or maybe you're adding them all up and dividing by 3. It's important whenever you're doing this sort of calculation to be able to assess which are the pKs that matter. Now, for your exam, when you're looking at this sort of thing, play around with things. Don't just go with AFK. How much would the PI change if instead this peptide was KFA or KFR? Any sort of variation. Give yourself that sort of practice problem. Use the exact same process that I just went through, but change those numbers and think critically about, do I need this pK? Yes or no? Okay, now question below. Which option below shows all of the possible charges that the polypeptide SAWN can have? It's almost like I misspelled swan. SAWN. Okay, for this, I have to think about, or the way that I approach this is I draw a nice little box right there, like right there. And I'll think about all of the identity of my amino acids. Serine, well, that can be positively charged on the N termini. The R group of serine, no matter what, is going to be, well, it's going to be neutral. Because serine, if we scroll up here, we'll see that serine is a diprotic amino acid. Now, going back, okay, the N and C termini of S, I only need to worry about the N. Next up is A, alanine. That's a diprotic amino acid, so I don't need to worry about those. W, tryptophan. That is a non-ionizable or a neutral, it's a non-polar amino acid, so that has no charge. And then we're left with N, asparagine. Now, I like to use N because people have a tendency to think about asparagine and think, oh, well, that's like aspartic acid. And heck, it's got a nitrogen, it's got to be protonated. And the correct answer is no, it's not. That's not an ionizable R group. In which case, yes, it is a polar uncharged residue. Or sorry, keep in mind, let me rephrase that. Keep in mind that asparagine is a polar uncharged amino acid. So then that leaves behind my C termini of asparagine, and that's going to have no charge whatsoever. So effectively, I have a molecule that whenever it's fully protonated has a +1. When it's fully deprotonated, has a charge of -1, because the only ionizable groups are the N termini and the C termini. Now, again, this sort of question, give yourself a little bit of a challenge and change that question. Rather than SAWN, what about if you had SRKQ? How does that change? Or KRSQ? Think about that sort of thing whenever you're answering this sort of question and you're going through this practice problem. Next up, denaturing a protein. Again, this is still our old stuff. Denaturing a protein requires a variety of reagents. If you wanted to disrupt hydrogen bonds, which reagent would be good to use? We have urea, dithiothiotol, and water. Okay, water is a little bit of a decoy. That's out. Now, none of these would be productive. We'll wait and see. Dithiothreatol, what's that effective for? That's effective for disrupting disulfide bonds, covalent disulfide bonds. Last but not least is urea. Urea and guanidinium hydrochloride are both good reagents for disrupting hydrogen bonds.
Oh, this is what might be helpful. Okay.
So urea and guanidinium hydrochloride, those both disrupt hydrogen bonds. Those are chaotropic agents is what they're referred to as. Now, next question. If you were curious about the likely secondary structures that a protein or polypeptide can form, which of the following would be your best piece of data and best piece of evidence? You've got a Dyson Knight cartogram, a Ramachandran plot, change that to capital R, a hydropathy plot, and a Chow-Fasman propensity plot. Well, hydropathy plot tells you about the hydrophobicity of amino acids. A Ramachandran plot tells you about phi and psi angles. And a Chow-Fasman propensity plot tells you about the likely structures that individual amino acids have. A Dyson Knight cartogram, I just made that up. Okay, the next question reads, an alpha helix consisting of 12 complete rotations is. So an alpha helix consisting of 12 complete rotations. Sorry, I had some technical issues here. I've got my piece of paper that I'm going to be working on. And this is, we've got a couple different options. 64 angstroms tall, 12 angstroms tall, made up of 24 amino acids or made up of 12 amino acids. So this question is kind of asking two different but similar things. So if we have one rotation, that is 5.4 angstroms tall. And that requires 3.6 amino acids. So those pieces of information are valuable. Now, 12 rotations. 12 times 5.4 equals, drum roll, calculator. It's going to be 60, and then 0.4 times 12 is 4.8. So 12 times 5.4, 64.8. I'm going to go ahead and change this to 64.8, give it a more precise and accurate number. 12.4, I'll change that in, and then looking at the other options. Okay, so 64.8 is the correct answer. That's what we were looking for. But then if we want to compare that to, well, 24 amino acids or 12 amino acids, well, one rotation is 3.6 amino acids. So 3.6 times 12 would be 37.2. 3.6 times 12. Oh, 43.2. That was way off. Okay, so 43.2 amino acids. So 24 and 12 are not good answer options, so that's where we arrive at that. Okay, next question. These researchers are responsible for assembling a scoring scheme for amino acids and their propensity to be found in a secondary structure. We have Chow and Fasman, Margaret Oakley Dayhoff, Christian Anfinson, and David Baker. Now, there's a little bit of a tell in that researchers is plural, but if you've taken the SAT or ACT or most standardized tests, that's the sort of thing that you are kind of suggested to not pay attention to. But regardless of that, the correct answer is Chow and Fasman. Now, next up, allosteric proteins have two different forms. I'm going to add to that question. They are best identified, or they're most commonly identified as T and R, A and B, alpha and beta, primary and secondary. T and R is the correct answer. I'm going to update that question because I changed the wording. I didn't change that one. Okay. Which of the following is an example of an interaction that can stabilize the tertiary structure of a protein? Okay, an example of an interaction that can stabilize the tertiary structure. Okay, so our tertiary structure is stabilized by hydrogen bonding, hydrophobic interactions, ionic interactions, basically any type of both covalent and non-covalent interaction is going to stabilize the tertiary structure. So we've got which of the following is an example of an interaction? I'm going to say between, and yeah, I'm going to edit this, between amino acids, and then I'll put in parentheses, and is correctly identified. That can stay identified. Okay, we've got ionic between aspartic acid and lysine. We've got ionic alanine and lysine. Alanine's a nonpolar residue. Ionic lysine and tryptophan. Tryptophan's a nonpolar residue. And then ionic, last but not least, alanine and tryptophan. That's two nonpolar residues. Now, if this was identified as a hydrophobic interaction, this would be correct because alanine and tryptophan will interact through hydrophobic means, but they are not an ionic interaction. Excuse me, that was gross. I apologize. The primary structure of a protein is stabilized by A, peptide bonding, B, R group interactions, backbone hydrogen bonding, and none of these are correct. Peptide bonding is correct. A low P50, low is in quotes, indicates the oxygen binding protein in question can bind oxygen with a high affinity. And then this is not necessarily a true false, but a kind of binary question. The oxygen binding protein in question can bind oxygen with a low affinity. So low P50 indicates a high affinity. So that is the correct answer. Click update just so I can close that down. The appropriate units for P50 are torr is the correct answer because that's one of the units that we use to measure the partial pressure or the pressure of a gas. The other options are moles, kilograms, milligrams per milliliter. Next up is myoglobin's oxygen binding curve, I'm gonna say, or oxygen binding is best described as cooperative, non-cooperative, positively cooperative, negatively cooperative, and none of these. The correct answer is non-cooperative. To change that question up a little bit, hemoglobin's oxygen binding is best described as positively cooperative. Carbamation is a post-translational modification when CO2 binds to the iron ion within a heme ring. True or false? And that is false. The reason that's false is because carbamation is a particularly unique post-translational modification where CO2 is bound to or added to the N-termini of the protein. I'll update that question. Next up, the shape of a MB or myoglobin binding curve is best described as hyperbolic, sigmoidal, exponential, and none of these are correct. The correct answer is hyperbolic. Now, if you were to take that question and make a little tweak to it, well, the shape of a hemoglobin binding curve would best be described as sigmoidal. Carbonic anhydrase functions in the lungs only. True or false? And that's false because carbonic anhydrase is going to function in the bloodstream so that it can basically feed. It's going to feed from the muscles, one place that it's going to be acting, and the lungs being the other. So false is correct. False is the correct answer here. The structure of hemoglobin is best described as a dimer of dimers, a heterodimer, a heterotrimer, and a homotetramer. Well, it is a dimer of dimers. What is BPG? A naturally occurring compound that stabilizes the T state of hemoglobin, a compound that competes with O2 for binding sites near iron in heme, a compound that competes with iron within the heme ring, and none of these are correct. It's a naturally occurring compound that's going to favor the T state. Now, if you remember in lecture, we talked about BPG and its role and its affinity for, or lack of affinity for fetal hemoglobin. In addition to that, where it fits, it favors that T state because that's where that central cavity is going to be found. I'm just kind of scrolling ahead to see how many questions I have left. All right, next up is an oxygen binding curve shifting to the right is indicating that, or is an indication that the T state is favored. A shift to the left would be the R state, and the answer options of the T state is favored, the R state is favored, neither the T nor the R state are favored, and none of these answers are correct. The T state is favored is the correct answer. Next up is approximately what is the P50 for myoglobin in the graph shown below? Okay, so this graph shows us, well, our it has our myoglobin protein indicated, and what we're looking for is our 50% point right about here. And so we want to draw that down. My drawing isn't particularly good there, so I'm going to clear all my markings there. And I'm going to refresh this and say, okay, well, if this is our 50% point, then we go all the way down to approximately, oh, there. And so we're just a little bit under 10 as an approximation. I'm going to clear my drawings. If we're under 10, well, which of these is under 10? 8. Is it 8.5? Maybe, but 8 is the best answer of the options that are presented here. I'll update that question. The observation that protonation of an amino acid within hemoglobin influences oxygen binding is known as, this is the Bohr effect. I've got the Bohr effect, the Randazzo-West consortium, the West-Davies effect, and none of these are correct. Well, it is the Bohr effect. Which of the following is an example of a homotropic effector of hemoglobin? Okay, so a homotropic effector is an allosteric effector that is also the natural ligand for that protein. So hemoglobin's natural ligand is oxygen. Oxygen is also an allosteric effector. Now, what that means is that, or an allosteric effector influences the conformation of a protein as well as the binding affinity for a particular protein. So oxygen, or let me change that to O2, does that. Carbon dioxide, not the case. BPG, well, BPG is not a natural ligand, so it would be an example of a heterotropic effector. Similarly, CO2 would be a heterotropic effector. So I'm going to click there. Okay, the I band. Now, this is where we're getting into muscle proteins. The I band consists of, okay, so now this is an important distinction whenever you look at a sarcomere, which are the building blocks of muscle proteins. An I band is only actin. Now, it's kind of subtle because you might see actin and myosin, but an I band only has actin. So that leaves us actin and myosin, only myosin. No, none of these are correct. Only actin is the correct answer. Now, this is the boundary of a sarcomere. So a sarcomere is the kind of individual units of a muscle cell, and a Z disc is the correct answer. Myosin releases from actin when it, well, binds ATP, releases ADP, or binds ADP. The correct answer is that whenever myosin binds to ATP, then it can release from actin. Next up is enzymes. Well, enzymes catalyze thermodynamically favorable reactions. They catalyze thermodynamically unfavorable reactions. Now, that might be a tempting response to say that it's catalyzing thermodynamically unfavorable reactions, but the correct answer is that enzymes catalyze thermodynamically favorable reactions. So the reactions that an enzyme is going to catalyze, it's going to overall be favorable. So think about what would a question be that just kind of pertains to enzymes. Hexokinase is an example of, well, here's where we bring in the classifications of enzymes. Excuse me. Hexokinase is an example of a hydrolase, oxidoreductase, isomerase, or transferase. And the correct answer is transferase. Structural changes that occur during a reaction are best described with the term catalysis, kinetics, or catanetics, or none of these are correct. And catalysis is the correct answer. Kinetics is more concerned with the rate at which things are taking place. Okay, next up is an enzyme catalyzed reaction can be as much as blank times faster than the uncatalyzed reaction. And this, okay, so more than 10 times faster. And, actually, I'm going to change this because I don't really want any redundancies. As much as, um, I'm going to adjust these so that it makes a little bit more sense because I don't want faster, faster to be in the question. As much as 10,000 times faster, 2,000 times faster, or 10,000, or yeah, or 10 times faster. This is just a matter of the magnitude. And truth be told, it's like 1 times 10 to the 14th times faster. So this 10,000 is actually kind of undershooting it. But it is the best answer because it's the largest number. Organic cofactors are typically referred to as coenzymes, cosubstrates, prosthetic groups, or none of these are correct. The correct answer is kind of definition, a coenzyme. Now, coenzymes are not chemically changed in a enzyme catalyzed reaction. Is this true or false? Well, the net of the reaction that would be so a coenzyme is going to undergo some sort of change, but then it's going to be returned back where it began. Coenzymes are not chemically changed during in a chemically or an enzymatically catalyzed reaction. That would be false because they do undergo a change and then they return. Okay, so that wraps this up. Every single one of these questions. What I want you to do and what I want you to think about with respect to these questions is how could I change or how could I tweak this question to get it to ask about something else? For example, if the question asks about hemoglobin, well, then think about how that would apply to something like myoglobin, and vice versa. If this is a question about like the shapes of the graphs or shapes of the curves, think about that as something that's relevant and important to understand. Now, that's because it is relevant to an understanding of like how an enzyme behaves and how a protein behaves. If you see a sigmoidal shape to a oxygen binding protein or a protein ligand interaction, basically a binding study, if you see that sigmoidal shape, well, that's a great indicator that the protein that you're working with is an allosteric protein. And so you have some sense of this is what it does. All right. Well, I hope this is helpful, and I wish you good luck on the next exam. Some of this stuff we haven't talked about yet in class, but we're going to. So hang on. All right. Have a good one.